Hello, this is Andrew Blancardi from Ali's TA Group, and here we're going to talk about the percentage yield and what that means for our alum crystals. Okay, so here's the progress on our alum crystals. You can't tell very much, but they're growing to be a respectable size. And what's odd is like they seem to be taking a cubic shape almost. I don't know, it's very geometrically pleasing. Let's see if you could see it better. Okay, you can see them accumulating at the bottom right there. So what's happening here is there's a nucleation site at the corner right here. So once one crystal is grown and set in that nucleation site, it makes it easier for the rest to follow in that crystal structure, allowing them to grow to bigger sizes much quicker. Okay, now moving on to the percentage yield. So we started with 1.02 grams of aluminum foil, and we ended with 24.25 grams of alum. Now that doesn't exactly equal like what we wanted to find, and so starting off we had the 1.02 grams of aluminum, and to find the moles of aluminum in that piece of aluminum foil, we divided by the mass of aluminum per mole. And so we found out that there's about 0.0378 moles of aluminum in that sample of aluminum foil. And since there's a 1-to-1 ratio of aluminum to alum based on this right here, the chemical equation of alum, as you can see, there's only 1 mole in this entire, this basic building block of alum. And so since there's only 1 mole of aluminum to 1 mole of alum, we can assume that we would be able to produce 0.0378 moles of alum from that aluminum. So based on that, we multiplied by the grams per mole of alum, which gave us 17.93 grams of alum to be expected. Now, that's not what we got. We got 24.25 grams of alum, resulting in 135.2% percentage yield of alum, which seems kind of absurd because that, like, how can we produce more than what we physically could? But this can be explained because of water's very sticky property. So water's polar, meaning that it has a positively charged side and a negatively charged side, meaning that it can stick to things very, very well. In our case, we washed the alum excessively, meaning that throughout this process, water probably got stuck inside of our sample of alum, accounting for the huge extra weight. So about like 7 grams of water were probably in between the alum. A way we could have potentially avoided such a high percentage yield would be to have dried the alum sample we had before we dissolved it again. So that would have caused it to get rid of a lot of the water that was stuck in between it from all the washing, which would have made a smaller reading in terms of the mass, making it more accurate in terms of alum, and since a lot of the water molecules would have been dried off of it. And that will conclude my presentation for today. Thank you for stopping by and watching my alum children. Thanks.